Hello there, I am Aditya, and in this video we are going to look at algorithm for lane detection with sliding windows using OpenCV in Python. So before we start with this, I'd like to clear the expectations out of this algorithm, what you could expect out of it and what try to create an autonomous vehicle out of it, because that will be too naive and disastrous for others. But however, you can use this algorithm to integrate into robotics and do something great in that field. So let's begin. In this directory, I have a file lanedetection.py and a video lanevideo.mp4. What we will do is, first of all, we will break the entire program into stages. For the stage 1, let's try to read the video file using OpenCV with our Python script. I'm going to skip that part out because that is not directly in interest with what we are learning here today. Alright, here we have the code for reading the video file that is attached in the directory. So when I run this program, Python is able to access, process, and even display the video file through the use of OpenCV library. So now we will be moving on to the next stage, and that will be marking the region of interest for the lane detection purpose. So again, it is not directly in our interest, so I have skipped the coding part. What we have on over here is we have 4 points, 4 coordinates, and I've used circle tool to plot them on our frame window. So with these 4 coordinates as the vertex of a quadrilateral, a trapezoid is formed, and that trapezoid is our region of interest. So we will be looking or doing image processing inside this quadrilateral or trapezoid, because rest is trees and sky, which are not needed for the task of lane detection. So we have the region specific to which the lanes are being passing through, and we want to do the processing in that region only. In the code from line 10 to 15, we have 4 vertices defined: TL for top left, BL for bottom left, TR for top right, BR for bottom right, and below them there is the code for um, adding the circle to corresponding points on our frame window. Now, for us to be able to perform lane detection with precision, it is essential that we are able to obtain or perform the task on the most efficient perspective of the video. Right now, the video is from a camera that is placed somewhere on the dashboard of the car, and therefore we are looking at the road from the dashboard, and that gives the lanes being coming in a trapezoid kind of region. But it would be more efficient if the camera were placed directly perpendicularly upwards from the road, and looking directly downwards on the road at a 90-degree or a perpendicular line. That is a kind of a bird's eye view, like a bird is flying over the road and looking perpendicularly downwards. That would give a better perspective, and we will be able to perform the lane detection task with more precision. So to be able to do that, we need to apply perspective transformation, and that will be our next step. Alright, I have applied the perspective transformation, and since it is a prerequisite for lane detection task, I have skipped the coding part. However, if you are not familiar with how perspective transformation is applied on OpenCV, you can check out the link in the description. And if you want to further know, look into the mathematical aspect of how perspective transformation works mathematically, again, the link is in the description as well. So now when I run the program, I have 2 windows. One window has the original uh, video feed that is coming from the camera being placed on the dashboard of a car. We have marked the region of interest, and then on the second window, bird's eye window, what we have is the different perspective of the video that we obtained by applying perspective transformation. So now we have the top view of the road. Let's proceed with detecting the lens next. To begin with lane detection, first of all, we need to be able to perform image thresholding on the video such that we are able to separate out the lanes from everything else. I'm afraid this again is going to be a prerequisite and therefore I have skipped the coding part. However, if you are not familiar with image thresholding on OpenCV in Python, I have left the link in the description. Um, Feel free to check that out. So here I have the code for track bars that will allow me to threshold the image in real time. And over here I have created those track bars. So without further any explanation, let's just run the code. And now we have on the right side the threshold image. And over here with these track bars, I can uh, optimize my thresholding values. So as I change the track bars, the threshold output changes in real time. So I can use these track bars to precisely threshold the lanes. So I have already done the thresholding and I have put the acceptable thresholding values. Now let's move on to the final step, that is applying the sliding window approach. So finally we have arrived to the final step, and let's take this one slow. So what we have is we have a mask window which has white threshold lanes and everything else is black. So basically the mask window contains of pixel values either 0 or 255. 0 corresponding to black and 255 corresponding to white. So what we want to do is we want to get the coordinates of the left lane and the right lane. And we want to make sure that we get it separately. We want to be sure that this coordinate is for the left lane and this coordinate is for the right lane. And how are we supposed to do that? Well, to do that, what we will do is we will use histogram. And what it is exactly is what I'll show you. So let's code for histogram. What we have is histogram equal to numpy.sum mask dot shape 0 divide by 2 colon comma colon comma x is equal to 0. So with this line of code we have created a histogram, and that histogram takes into consideration only the bottom half of the mask window. What is bottom half? So in the mask window, let's say along the y-axis we have from 0 to 700. What we have done is we have divided by 2. You can see mask dot shape 0 divide by 2. What we have done is we have taken into consideration only the bottom half, that is, let's say, from 350 somewhere around to 700 units. So it will plot a histogram along the x-axis, that is axis is equal to 0. So it will plot a histogram along x-axis, and that histogram will have peaks uh, at x coordinates where the intensity of pixel is high, in the sense where the pixels are white, that is where the lanes are. So we are going to get peak values at x coordinates where the lanes are present. So that was the purpose of drawing the histogram. Now let's move on. So now what I need to do is I need to separate the left lanes from the right lanes. And to do that, I'll create a midpoint variable that will be numpy.integer histogram.shape 0 divide by 2. And what this is supposed to do is we are going to it is going to hold, this midpoint is going to hold a coordinate that will be somewhat according to this picture on the right, somewhat 1200 by 2, somewhere around 600, and we will use this midpoint to separate the left lanes from the right lanes. Now I will do the lane detection for left lane, and that will be left base. So the left base will be numpy.argmax histogram colon midpoint. So what it is going to store is it is going to store the x coordinate to which there is a peak on the histogram before the midpoint. So that will be somewhere for our case around 400. Similarly, the right base will be numpy.argmax histogram midpoint colon plus midpoint. So that will be considering the right half, that is from midpoint till the end, and the x coordinate in that range which has a peak in the histogram will be stored in the right base, and there will be a plus midpoint for the for so that we have the reference from the origin, that is 0. Now the use of histogram has saved us the trouble of dealing with the noises. For example, in our case, on the right half, for detecting the right lane, we have two candidates. One is the right lane almost at 800, and there is another peak at 1200. And assuming that 1200 is the noise, it is not being considered. And how is that? Because for the right base, what we are doing is we are taking the argmax. So we are going to take the x coordinate corresponding to the highest peak. So even though we have two peaks in the right plane for, or we have two candidates for the right base, what our algorithm does is it is going to only consider that one which has the greater value or greater peak, stronger white intensities at the x coordinate. So automatically the candidate at 800 is selected and the candidate at 1200 is neglected, and probably it is noise and we do not want that. So now we are done with histogram and we have the coordinates of left base and right base. So basically we do have the coordinates of the left lane and the right lane. But there is still something missing. And what is that? Well, we have missed a major thing, and that is the variation in the x coordinate or the variation in the location of the lanes of left lane and right lane as the y coordinate varies. That is, what we have done is we have considered only the very bottom of the screen, that is at y is equal to 700. We have measured the peak of the pixel, and that corresponds to left lane and right lane. But the lanes are under no compulsion to be at going perpendicular upwards. They can be curving inwards, curving outwards, and that is a problem because you can see that in this case the lanes are curving rightwards. So whatever maybe the pixel, maybe the coordinate for uh, coordinate of x at y equal to 700 will change as we go upwards or as the y coordinates moves towards 0. So let's say at y equal to 300, we see that the x coordinate is shifting towards right, and we have to capture that. And how do we do that? For that we need sliding windows, and that is what we will look at up next. So to begin with sliding windows, I'm going to define three variables: y, lx, and rx. Y is equal to 472. That is nothing but the height of the rectangle that we are presently at. Lx and Rx will be empty lists, and I will use these to store the x coordinates of the left lane and right lane as we move above towards 0 on the y-axis. So uh, currently we are at y is equal to 472 and we have the left base and right base value. I'll append those to Lx and Rx, and then I will move upwards by the height of the rectangle. Let's say we are taking the sliding windows, number of sliding windows to be 12, and therefore each sliding window will be of height 480 by 12, that is 4040, that is 40. So what we will do is in the next iteration we will make y is equal to 472 minus 40, that will be 432, and for that again we will update the left base and right base, and we will append those to Lx and Rx, and as we move upwards, that is towards 0, we will keep appending the left base and right base x coordinate values to Lx and Rx respectively. Now I will make a copy of mask and I'll name it as MSK, and on this frame MSK I will be drawing the rectangles, that is sliding windows. So let's proceed with making our loop. So while y is greater than 0, what we want to do is, first of all, let's do the threshold for left lane. So image is equal to mask y minus 40 colon y comma left base minus 50 colon left base plus 50. So basically image contains only the content inside the bottom left rectangle. Then I'll detect the contours. So for that it will be cv2 dot find contours image comma cv2 dot return tree comma cv2 dot chain approx simple. With this line of code, I'll be able to detect the contours in the bottom left window, that is the left plane window that is marked 1 on the image on the right side. Now, I'll be iterating over the contours that are detected in that sliding window or rectangle. And for each counter, I'll get the moments by m is equal to cv2 dot moments counter. And if the value in m0 is not equal to 0, then I will just get the center of mass coordinates x and y and store them in variables cx and cy respectively. So now cx and cy are the x and y coordinates of the lane detected in the particular sliding window that we are dealing with, or that rectangle. And interestingly, we only need the x coordinate because we don't care about the y coordinate because we are inside a rectangle of y equal to 472, and we are only interested in where the lane is along the x axis. So we have to make sure that this cx, we are able to get it from the perspective of the window. So to do that, we need to get the reference from the origin, and origin is at the bottom left. So what I will do is I'll append left base minus 50, so I get to the bottom left, and then I will add cx, that is the center of mass x coordinate of the lane detected in that sliding window, in that rectangle. Once I've appended it to Alex, I'll also update the left base variable. So left base now becomes left base minus 50 plus cx. So when I move on to the next rectangle in the next iteration, the left base will have a different value, and that will depend on the previous sliding window. So for the right lanes, I'll just copy this code for left threshold, paste it below it, and make adjustments for the right threshold. So everywhere in this code, wherever we have left base, it should be changed with right base. So we have one here, over here, this one, here, and here. I'll change them with right base, and now this will detect the lanes in the right half of the screen, and those will be the right lanes. So yes, the code looks good. This should work. So let's proceed with drawing the rectangles on our MSK MISC window. To draw the rectangle, we have the command cv2.rectangle, name of the window in which we are supposed to draw the rectangle. So MSK, then the coordinates of opposite vertices. So left base minus 50 comma y That's one x comma y coordinate of left base, left vertex, and then the opposite vertex that will be left base plus 50 comma y minus 40. So we have our rectangle. Then we need to give a color to our rectangle. So that's going to be white. So in RGB it is 255, 255, 255. And the boundary of the rectangle should be of thickness 2. I'll just copy this and paste it, and this time it is going to be for the right base, that is for right lanes. Now let's make sure that the window MSK is being displayed when we run the program. So for that we have cv2.imshow, name of the window that will be lane detection, sliding windows, and that window will be MSK. A couple of quick corrections before we run the program. In the while loop for y greater than 0, at the end of it, we want to decrement the y by a value of 40, that is the height of the sliding window. And for the right base, it should be right base plus midpoint because it is in the right half of the window. So with that, everything looks good and we are ready to run the program. And there we have it, lane detection with sliding windows in Python using OpenCV. If you found this helpful, do show us your support by subscribing to this channel. And if you found something problematic, do let us know in the comments. And with that, I'll take the leave. Thank you for watching this video.